wondering if there was any I wonder if there was any additional information about the RISD conference.
Uh, from what I understand, it will be in September and it will be in Tasmania.
Okay, so not gonna be in the summer. Our summer, their winter.
Yeah. Uh, we were originally looking at like December, uh,
Uh-huh.
their summer. These things tend to be like a year and a half apart where they oscillate from north to south. Uh,
Right.
it's not my conference, it's Michael Fitzgerald's, but
I figured as much. Yeah, I
yeah.
should Michael.
But December can be tough because the Australians go on vacation from like December 15th through January 15th, and it is like absolute vacation. No one can be reached. And so for various reasons, they wanted to move it to September, which puts additional
Okay.
pressure on us because we wanted Tasmania because that's where our radio telescope effort for the MWU curriculum is centered. And
Hmm.
it looks like the radio telescopes will be ready, maybe
Oh,
within a month. They're getting really close. So the pressure is now on us at Skynet to make sure Skynet 2 is ready to receive them by September. I think we will be, but it's a
okay.
challenge.
Absolutely.
So I was going to
So
start the meeting with Kent, what's broken now?
Actually, I just figured out that, because I'd asked about giving students feedback and stuff, and the only way I can get that to work myself is to make a copy of your assignment, and then it gives me editing privileges. Otherwise, when I go to save it, it doesn't save the feedback option.
By feedback, you mean you talk about the surveys?
Like, no, when they click on when they do a submission, it
Oh, right,
doesn't.
right. I remember now. Yeah.
And so the only way I can get that to work is to copy the
Okay.
assignment, and
Okay.
that puts me in editing mode.
Okay. Yeah, and some
When
people do that and they run their own. That's totally
yeah,
fine.
when you set those up, do you make new assignments for every individual?
Yeah, for each class, I make a copy of the assignment so you can tweak things. Um, and most people just run with the sections I set up, but some people want to run their own, so they then copy from mine to theirs, and that way you get any updates.
Okay,
If you copy from the one that you just created, technically you still should get the updates. They're supposed to propagate. Uh,
okay.
so you could go either way. All right, so this is our last meeting of the semester, up to Lab 9. But I figured I'd start with another sample from the MWU curriculum. And most of the stuff in the MWU curriculum is Skynet based, though there are two tools that we've built that are not. For whatever reason, I decided to feature those. So a few meetings ago, I showed you our HR diagram tool, which can use Skynet data, but doesn't need to. You can grab data from Gaia, et cetera, right from the data repositories and do your HR diagram analyses on it. So it's kind of exciting because there's schools that are incorporating Skynet, but there are many, many schools out there that don't incorporate Skynet, and this would just be an awesome tool for them to build in when they're teaching HR diagrams. And so we have another one like that. It's in development, so it's going to be better soon for some value of soon. This is gravitational wave analysis. So I'll show you what we have at the moment. Let me move you over here, share my screen. This the zoom controls out of the way and then spread you out. Okay, let's see. Um, so gravitational waves are super sexy. And I'm not going to do like a full how I would explain this module to an MW user, just give you a few tastes of it. But it's a very hot topic in astronomy right now. Here's the one of the, actually, this is the Virgo detector. Is that right?
that's
Virgo
what it says at the
detector.
bottom.
Yeah. Maybe this one's LIGO. No, that's also Virgo. Doesn't it, maybe this one's LIGO. No, that's the same as this. Okay, we're on the LIGO page, but they're featuring the detectors, but it's basically, get the idea. It's a giant interferometer. The lengths are 4 kilometers. So you got two arms. I think they're 4 kilometers long. It may only be three for Virgo. I can't remember. There are two LIGO facilities, Louisiana and Washington State. Virgo's in Europe. The Japanese are working on one, though it had a lot of damage from earthquake, was it? Uh, but anyway, so in MWU, this is getting near the end where we've done star formation and evolution. We did the solar system before that, and now we're into star death, and we've done planetary nebula astrophotography and pulsar stuff in the radio. So now I want to get some black hole stuff. And we have black holes in the radio, like supermassive black holes. There are things we do with that throughout the curriculum. But this was just too cool to pass up. Even though it's not Skynet data, we decided to build a mini version of the gravitational wave analysis tool that the professionals use, but build it in such a way that students can use it. So, the idea is, again, I know you know this stuff, but, just quickly, you have two objects going around each other. According to Newton, they'll go around each other forever. But according to Einstein, the orbit will decay, and eventually you have a merger. And as you get close to that final stage, it's really cranking out the gravitational waves, and they propagate through the universe. And they can interact with this detector from any direction, including up through the Earth. But imagine they're coming down orthogonal or up orthogonal to the detector, just to simplify it. What that does to the detector, it has the two arms and makes one short and the other long, and it kind of oscillates as the wave goes through. Not to the scale that I'm showing, it's like almost atomic, maybe subatomic differences in scale. I can't remember, but very, very small. But that's why you have an interferometer running through these tubes. The light is split, goes up, comes back. And if one tube is longer or shorter than the other, it's out of phase, and we can measure that very precisely. Okay, so you're measuring these distortions in the space-time continuum, which is kind of a cool thing for students to think about. Now, to analyze that data and get masses is really tricky. There's, tons and tons of code and models that have been built, and we built a mini version of this. Now, this is on our old tool site. You may have noticed going through the labs, when students click on the tools, it gives them an option, the new tools or the old tools. This is still on the old site, and hopefully we'll rebuild it and put it on the new site pretty soon. And also right now, this tool only, the back end that does the processing only works for one at a time. I mean, you could have many at a time, but they queue up. And to process a data set takes about 2 minutes. So you can imagine doing this in a classroom setting, it would be a disaster. So we're expanding our back end to cache. There's only a finite number of these things. And once they've been processed once, we can cache the result. So whenever anyone else requests it, we just give it to them and don't have to recompute it. And every couple years when LIGO and Virgo add new things, then, it'll be slow for the first one that's processed, but fine. So it has a link to the LIGO Virgo page, the event list. Maybe I'll hop down to the very first one of any significance. Here it is in 2015. And these are, pretty massive black holes. It's kind of like the story of exoplanets. When we first detected exoplanets through the Doppler technique, it was a surprise because what we were picking up were hot Jupiters, gas giants right next to the star, which gives you a really strong tug. And we didn't expect those to be there, so we didn't expect to have those strong tugs, and our instruments weren't sensitive enough to get a solar system Jupiter star, the Sun Jupiter detection. So it was a surprise. And this was a little bit of a surprise. We didn't really know if there'd be binary fairly massive black holes out there. It turns out there are. And so in 2015, we started picking these things up. Here, I'll just click on this one. You can see the data products. H1 is one of the LIGO sites, L1's another one. If there's Virgo data, they have that stuff as well. And you pick one you like. That what we're looking at here is this is time. And so you can see tenths of a second. And this is frequency. So this is the final instant as they're getting closer, faster, faster. And so there's the frequencies going up and the intensity is going up, and then it merges, becomes spherically symmetric, and then it emits no more gravitational radiation. So you can grab the data. It's the first one, 16 kilohertz HDF, and come back here. And again, it's just the old site using the tool called Gravity Pro out of all the tools there. And you load it in here, and you got to be patient. It takes, this one comes up in about 30 or 40 seconds. This one takes about 2 minutes to generate. But once we have the caching built in, as long as someone's done it before, it should be fast. And again, we'll put this all on the new Astromancer site as soon as I can spare someone. All my programmers are working on Skynet 2. Now, I've already kind of fit this one, so let me undo got the hiccups results here. So, purple. Well, okay, we have these two things: frequency versus time. This is called the spectrogram. And then down here we have strain versus time. This is the actual oscillations. So you start with the spectrogram, and they run millions and millions of models. I think we have 250,000 models that we generated ourselves using the LIGO code. This is all powered by LIGO code, but just with a much smaller set of models that we're comparing to keep it fast. So total mass, you see there's a curve here. Frequency, so the higher the mass, the lower the frequency. So you can adjust the frequency. It's a little too sensitive, the buttons. You can adjust the time. I'm just going to do it here. Let's lower this total mass. It's not bad. Maybe a little bit lower. Sometimes you get a little graphing bug there. Push the time forward a little bit. See if I can get out of that little plotting bug. No, it's kind of stuck there now. It's not supposed to fill that in, but you get the idea. I got to push it forward. We'll put fine control buttons on this. Okay, that's pretty good. You got to ignore how it filled it in. That's just annoying. You also have the mass ratio, which changes kind of the shape of it. High mass ratios, it's a little flatter. So anyway, you get the idea. You could play with the merger time, the total mass, the mass ratio. So you're solving for the mass of the two objects. Then down here, if it's a significantly bright event above the noise, you can see it. You can zoom in here. We could do some little adjustments like phase. Kind of line it up fairly well. And then there's the distance to the event. And that affects how strong the oscillations are. Anyway, you can, the models aren't perfect. They'll be good right up to ring down. They get a little messy after, during the ring down, and they'll fall apart. If you go too far in advance, they'll get a little bit out of phase. But this one's not too bad. You can imagine spending more time than I did here. And so you get a measure of the masses and a measure of the distance to the object, which is pretty cool. They can do this themselves. Right now, only LIGO professionals with this code base installed can do this. And this is something any student can do. And so the tool is almost ready. And the rest of the MWU module around this will focus, they'll do a couple of these, or everyone will do, one of their choosing. And then we'll give them the neutron star one in 0817. So 2017, April 17th. Two neutron stars, unusually nearby. So freak lucky accident, it turns out. Sadly, because we've been looking for years, raising money from NSF to go back, but there just hasn't been another one like it. But two neutron stars merged. And this gives you an extra advantage because when two black holes, two things you can't see merge and make something you can't see, then you can't really figure out what galaxy it's from. These things are localized poorly on the sky. But if two neutron stars merge, then you get a gamma ray burst. And with a gamma ray signature, which narrows it down, and an optical signature, which really narrows it down. And it narrowed it down to, well, so I'm sorry. The gamma ray burst can narrow it down, and the LIGO triangulation can narrow it down, but there's still going to be a bunch of galaxies in there, like 30, 40, 50 galaxies. And we just imaged all of them with prompt. And we're the second group to find it out of the six that made it in the paper. And so the tail end of this activity is they'll do the neutron star event. I won't load it now because it takes 2 minutes to process. It's a much slower merger. And unfortunately, it's sub noise. You can't get the distance. It's all beneath the noise down here. They'll get the mass. They'll realize, oh, it is a neutron star. We'll give them the distance you can still extract it from more powerful tools. And then we'll give them the 30 galaxy images, and they can split them up amongst themselves and with both pre and post event images, and they'll hunt through them as a class, finding the one with the counterpart. Once they have that, they have the redshift of the galaxy. We gave them the distance. They can measure Hubble's constant. So the reason I'm showing this one today is we're going to measure Hubble's constant using the final OPIS capstone is measuring Hubble's constant using traditional cosmic distance ladder techniques. But this is a technique for the local universe. It's independent of the cosmic distance ladder. So it'll be a check on like type 1a supernovae, tip of the red giant branch, and these local techniques. Because you're all aware of the Hubble tension. The CMB gives a number in the high 60s, and local measures like type 1a supernovae in the low 70s, and they're now 6.2 sigma discrepant. And so there's something wrong with our understanding of the universe. Perhaps. Anyway, we'll get back to Hubble tension. But anyway, this was going to be the capstone lab for OPIS. But when I realized that we can actually get spectroscopic redshifts from the radio telescopes, then I went back and did a traditional cosmic distance ladder measure of Hubble's constant, where you measure a speed, you measure a redshift, gives you the speed. You measure a distance using like a Cepheid, which they've learned how to do. The ratio gives you Hubble's constant. But here in MWU, the more advanced curriculum, they get to do a more advanced way of it. Anyway, just want to share that with you. It's a tool that's out there. You can use it now as long as you don't have a ton of students use it simultaneously. And within a couple months, you should be able to do that as well. Questions on this?
Yeah, did you have to upload that? I was trying to follow along with you. Did you have to upload the data file?
Yeah. You
get to pick whichever one you want from that GWOSC event portal.
You download the 16 kilohertz, 32 seconds. So the first one here, HDF.
Okay.
What you download. You upload it here, and then you got to wait. But after we have the caching built in on server side, you won't have to wait more than a few seconds.
Right. I think you said that. I was trying to follow along. Sorry. Okay. And then, so can you say?
Yeah, and you work with Chuck, so you're interested in this, I'm sure.
Yeah, absolutely. So can you say some more? I actually haven't followed along closely. Do you know where we are with the with measuring the Hubble constant from gravitational waves? Because that is one of the really exciting aspects of it, to like try to get out there and have a third way of measuring the Hubble constant.
You have two ways you can do it. One is you build up a large enough statistical sample, and then you can no, that may not be right, because you still need the distances. No, that's right. Okay, so with these gravitational wave events, you get a measure of the distance just from the gravitational wave data. but there's a sign I uncertainty. Depending on the angle of the system, the distance is uncertain.
Right.
And so if you build up like a couple hundred of these, you could do a statistical analysis. They're not quite there yet. The
Okay.
other approach is you get an optical counterpart and it has a gamma ray burst. So it has to be enough on axis that you have a gamma ray burst and an afterglow, which we had in 1708-17. And that when that afterglow peaks, we're used to gamma ray burst afterglows just fading because most gamma ray bursts we find from the gamma rays, which means it's pointed right at us, or else we didn't see it. These are more off axis, and so initially we don't see it, but as it slows down, becomes non-relativistic, it no longer beams its emission forward, but spreads out so you here at Earth can see it. So when that peak occurs, that gives you the inclination angle with some modeling.
Okay.
And people have done that with the 1708-17 event. It was easier because it's mostly on axis because we did see gamma rays from Fermi, and it gives you something consistent with the supernova values, but with a large error bar, plus or minus 8. you know. So that's
So
where we are at the moment.
is is that 2017 event the only multi-messenger event that we've seen so far?
With an yeah, yep, multi-mess, yep.
Yeah, because I think when that happened, it was so shortly after the 2015 gravitational waves. I would think a lot of us were sort of like, oh, we're going to see these all the time.
Oh yeah,
And now it's been 7 years and we still
yeah.
haven't seen it.
Oh, I feel like because I wrote a grant and I have about $500,000 from NSF to find the next one because we have the telescopes that can do it. We proved, but we came up short in 03, 04. So far has been a bust, and yeah, it seems that it was a lucky event, which is unlucky after the fact.
Well, it's still really really exciting. Like right now, I think especially with the Hubble thing, it's like really the field to be in. It's very
Yeah.
exciting.
And so we want to bring this into our survey classes because if you open up the textbook about gravitational waves, it's just 2 pages of fluff. And here you can actually get into it. Okay, anyway, let's measure Hubble's constant the traditional way. So let's see where we are in our tabs. So here's our video record, 1 to go. We'll be adding it after. Here are the videos for Lab 9. I haven't shot overview videos. This lab is new. We ran the OPIS curriculum with 8 labs forever. Just in the past year, I finally created Lab 9. Because the reason it took so long is if you want to measure Hubble's constant, you need a redshift. And I didn't realize I'd be able to get the redshifts with the radio telescopes, and I don't have any optical spectrographs on Skynet. And so I was trying to figure out some way to make the gravitational wave approach work, even though it's not cosmic distance ladder. It's independent of the CDL. But then I realized, yes, we can get redshifts of at least a few nearby galaxies with the radio telescope, learned how to do that. And then I was able to make this capstone lab. And yeah, so I don't have overview videos for it, but it is in WebAssign now. And it's a capstone for labs in the following sense, for labs 5, 6, 7, and 8. So in 5, we learned how to measure distances using standard candles, R-Lyrae Cepheids type 1As. Lab 6, we practiced that with R-Lyraes and Cepheids during the Great Debate of 1920. In Lab 7, we learned how to measure redshifts. They were Doppler redshifts, but same technique. Lab 8, we learned the true nature of the Big Bang and how cosmological redshifts are fundamentally different from Doppler redshifts. Now here we are in Lab 9. Having learned Hubble's law in the previous lab, we're now going to measure the slope, Hubble's constant, which gives us things like the age of the universe. And as you'll see, I've also built in a CMB track. So we're going to do Hubble tension. We're going to do the CDL and the CMB. Though some people opt to skip the CMB if it feels like too much. And so this does everything because we have to measure distances. We're going to give them some Cepheids. They know what to do here. They have to measure redshifts. They know how to use the radio telescope. So we're set. And now they understand the nature of the Big Bang from Lab 8. So we could pull it all together and do this cool thing. And so a couple how-to videos are embedded in the labs. Okay, so here's Lab 9. No, that's the WebAssign page. Here's Lab 9. Brought it up. So let's go through. Let's go through it. No more observations to place. It's the final lab. Okay, so goals. Use radiospectroscopy of nearby spiral galaxies to measure their cosmological redshift. Use Cepheid stars that we give them. They're not going to observe them, but like in Lab 6, we just give them some. They're going to use them to measure luminosity distances. Combine these, just the ratio gives us Hubble's constant. But then we're going to show them how to measure Hubble's constant from the CMB in a different way. In the background section on the CMB is a little extensive. But often we teach CMB in our introductory courses, so it's nice to have a CMB thing. If you don't teach CMB and don't want to do it, just skip part B. But I'll give you some background on the cosmic microwave background. And these two techniques are really antithetical in that cosmic distance ladder is the local universe, nearby measure, and CMB is as far away as we can get. So it's a global measure of the universal expansion and a local measure. And then for both or either of these, we show how to get the age of the universe just by inverting Hubble's constant gives you a measure of the age. Okay, equipment, just the computer. 3 background sections. Okay, we'll start with Hubble's constant from CDL, Cosmic Distance Ladder. So just by review, as we learned last time, all the galaxies except local things like Andromeda are moving away from us, and the farther away it is, the faster the apparent recessional speed is. But we learned it's not an explosion in space, it's due to the expansion of space carrying everything apart. So here is Hubble's law, CZ on the left. So C is the speed of light, Z is the fraction of the speed of light at which it appears to be moving away. So CZ is the apparent velocity. And again, you can have Z's greater than 1, so it can appear to be moving faster than the speed of light because it's not moving through space. Space is stretching. Hubble's constant is proportionality constant, and so here you have the distance. So CZ is measured in, so this is about the unit, because it's a weird unit, Hubble's constant. You got to explain it to them. CZ is measured in kilometers per second, luminosity distance in megaparsecs, and so the ratio right here will be kilometers per second per megaparsec. That's where that crazy unit comes from. It's just telling us for any megaparsec of space, it's expanding at a rate of how many kilometers per second. Again, it's very capstone-y because they learned the redshift part in 7 and the distance part in 5 and 6. Okay. So that's that. CMB, a little bit more background here, some of which you'll probably cover in lecture if you teach this there. I'll do it here real quick. Again, I know you know these things, but just kind of a quick encapsulation as you might present to a student. So we know the universe is stretching out, pulling everything apart from everything else. Imagine running the clock backwards. So instead of individual galaxies, you go far enough back, they all merge, and you just have this dense, hot gas. If you go far enough back in time, that's what you would get, a dense, hot gas. And it's dense enough to be opaque. And when you have an opaque gas, you get a thermal spectrum, just like stars. Stars are gas. We can't see through them. It's opaque. The energy in the core is being created at particular wavelengths and frequencies. But by the time it bounces around, you end up with a thermal spectrum. So opaque gases give you a thermal spectrum. And so every point in space is like the inside of a star. Throughout all of space, and it's emitting this light and immediately recapturing it and bouncing it around. It's opaque. The light can't get anywhere. It keeps running into stuff. But if you run time forward after 380,000 years, then it becomes transparent. The density drops, it becomes transparent, and the light is released from every point in space into every direction. So it's still here, just running around like crazy, no longer interacting with the matter. Now, a couple places in the lab, I have a few parentheticals giving some technicals that aren't necessary for the understanding what they're going to do, but you could get questions. So in reality, it's not just that the density dropped to the point of transparency. What happened is the density dropped, the temperature dropped, eventually it got low enough that you could form atoms. The protons, electrons combined. We call it recombination, even though it was the first combination. just a misnomer. And then when that happened, everything was transparent. So that's technically what happened, and the photons were released. And they were optical photons back then. It was literally like the temperature of the surface of a star everywhere. But over time, there's been a lot of time since 380,000 years. That's nothing. The universe has expanded 1,089 times. We can measure it very precisely. And so everything's been cosmologically redshifted. Those optical waves have been stretched out 1,000-fold, which puts them now in the microwave part of the spectrum, and hence the cosmic microwave background. And this is a fundamental prediction of the Big Bang. As I mentioned last time, the Big Bang is not a theory. We call it that, but it's a working model with tremendous experimental evidence. And this is one of those pieces. If it's a real theory, there should be microwaves bouncing all over the place. And in 1964, Penzias and Wilson discovered them by accident. They have a microwave horn here, and they were trying to make it low noise, but there was a noise floor they couldn't get below. And then after a while in talking with people, they realized that it was the afterglow of the Big Bang, the CMB, that they were picking up. And they'll never get below that noise limit because it's everywhere. And, another key prediction of the Big Bang Theory is this has to be a thermal spectrum. And for that, you got to go to space to get all the frequencies. COBE went up in 1992, and it's a perfect black body. Okay. So great verifications of the Big Bang working model. Now, here's where it gets a little more subtle. It's a perfect black body, but it can vary from point to point in space by a tiny amount. And the reason why is after 380,000 years, that was enough time for the dark matter to clump a little bit. Just 1 part in 100,000. That means you should have 1 part in 100,000 variations across the sky. So the CMB is super, super uniform, but these are maps of that 1 in 100,000 part variation. And you see it there. It's there just at the level predicted. This is COBE, WMAP, and Planck with better and better instrumentation. But you see the structure of the map improves. It's just the angular resolution also, it stays the same, but the angular resolution improves. Now, also in parenthetical, in case you get the questions, here are 2 questions for you that are answered. Why does the dark matter clump but not the normal matter? Where the normal matter interacts with the photons. So they're getting slammed in all directions all the time by the photons up until recombination and the light's released. And that kept the normal matter uniform. But the dark matter doesn't interact with photons, so it was free to clump gravitationally. And the second question you may get is how does that imprint the CMB if they don't interact? And basically, if you have these gravitational overdensities, as that CMB light tries to stream out, it loses energy. Just like if we send light off the Earth, it'd be gravitationally redshifted, it loses energy. And so that's why you see variations in the light. It's actually the dark regions, because when you gravitationally redshift it, it shifts the spectrum and we interpret it as a lower temperature. So the things that look like a lower temperature are actually the overdense regions, the blue, and the red's the underdense regions. Anyway, those are parentheticals because they're not super important for executing the lab. Now, how do we get Hubble's constant out of this? That was just background on what the CMB is, but how do you get Hubble's constant? If you zoom in, they're clumps. They're clumps on all scales, but there's actually one scale that really stands out, and we'll zoom in, you'll see it. The clumps all are around a degree. And it really stands out. If you've ever seen the CMB power spectrum, that first peak is really strong, and that peaks at 1 degree. I don't show power spectra in here. That's too confusing of a concept at the survey level. Okay, what causes those clumps? They have an angular size, about a degree, and any angle is equal to a physical size divided by a distance. So the physical size is set by pressure waves. As that dark matter starts to collapse, it sends pressure waves through this gas, and they move at the sound speed. So this is sometimes called the sound horizon, but I don't use that term because I don't want to confuse the students. The sound can mean different things to them. So I call them pressure waves, and the pressure waves can only travel so far. And so you get clumping on the scale over which these pressure waves can travel in this time. And that's R. It's a physical scale. And then the denominator, the distance, is the distance from us back to the CMB. And according to our simple equation, inversely proportional to Hubble's constant. But this equation is actually just for the local universe. If you want to go all the way back to the CMB, you have to build in the cosmological parameters omega matter, omega lambda, if you believe in a constant, um, a cosmological constant, which now the data is starting to show that's not the case. But that's an interesting aside that I don't want to distract us with. Maybe we come back to afterwards. But anyway, the real equation going far out is a little bit different, but still it's proportional to 1 over Hubble's constant. So how's this work? If Hubble's constant is larger, that means the distance to the CMB is smaller, which means these clumps will appear bigger. They'll be angularly bigger, like here. Or if Hubble's constant's bigger, the CMB is farther away, and so those clumps of that fixed physical size will appear smaller. And this is how they actually appear. So all you have to do is measure the size of the typical clump. And yeah, it does depend on all these other cosmological parameters, but I fixed them to the best known values. And you just measure the size of the clump in degrees and multiply by 82.2, and that's Hubble's constant. If it's bigger clumps, you would have gotten a bigger Hubble's constant. Smaller clumps, a smaller Hubble's constant. And this equation is good to about 8%. So that's our other way of measuring Hubble's constant. Again, you can run the lab without the CMB part, but if you want to do both, it's here. Last bit of background, then we'll execute the lab, is age of the universe. So Hubble's constant is kilometers per second per megaparsec. The kilometers and megaparsecs are both distances. If you do some unit conversion, you cancel it, and Hubble's constant is 1 over time. So flipping it around is time, and that time is approximately the age of the universe. Now, kilometers per second to megaparsec, per megaparsec, but the universe has expanded since the beginning of time. It expands a full each megaparsec. Yeah, so since the beginning of time, each megaparsec today is expanded a megaparsec. In the beginning of time, there's nothing. So under the approximation of a linear expansion, Hubble's constant is just 1 megaparsec per the age of the universe per megaparsec, or 1 over time. It sounds a little confusing, but basically, if the expansion is uniform, constant rate of expansion, Hubble's constant is just 1 over the age of the universe. So they just flip Hubble's constant. They have to do some unit conversions, get the megaparsecs into kilometers so they can cancel, and the seconds into billions of years, and we show them how to do that. Now, in reality, it wasn't a uniform expansion. Early on, we had a little bit of deceleration. When matter dominated, it worked against the expansion. Now we're into acceleration, as they learned in Lab 7, caused by dark energy, which we don't know what it is. It is that which causes acceleration. But overall, it's fairly linear, and so this is a good approximation. Okay. So for either technique, just inverting Hubble's constant gives us an age. Okay, we're done with the background. Any questions there? Okay. Procedure. So we started this a little bit last time because we submitted the observations last time, or talked about how to submit them. So in Lab 7, we just did like a 10-second integration. And we saw a whopping H1 signature from the Milky Way. But these galaxies are farther away. And so we have to do a minute integration, and we have to do on-off. Minute on, minute off. And I may have explained last time, but here's the reason why again. This is the galaxy M83. It's one that's not on their list. I think is that Virgo A? I can't remember. It's a Virgo cluster galaxy, so I've eliminated it from their list because it's not just Hubble flow, but other galaxies are tugging on it. or maybe it's not edge on. I can't remember. Yeah, well, that doesn't matter for this lab. Anyway, sorry. It's not on their list for some reason. But here's the Milky Way hydrogen, and they shouldn't be distracted by that. This is actually their signature. And these oscillations are instrumental effects, just the nature of the radio spectrometers. And so you can easily miss that signature. So you also shift the telescope 2 degrees over. I showed you how to place the observations last time, so I won't do that again. And here's the off spectrum, almost the same, except that little blip is missing. Now to bring out the blip, you subtract the two, this one minus this one, and you also divide by the off spectrum to correct for the response of the instrument. These variations are due to instrumental response. That gives you an on minus off divided by off spectrum. Looks like this. You won't get perfect cancellation of the Milky Way line, nor perfect cancellation of those undulations, but it does really bring out, now this tiny thing right here, you really bring it out, and so you can measure it. And first of all, we tell the students it should be a lot wider than the Milky Way line, because Milky Way, you're just going through a single line of sight. And so you're getting just a single blob of gas and has a single Doppler speed. But these galaxies, the full galaxy is fitting in the telescope's beam. So you're seeing the side of the galaxy moving towards you, which is blue shifted, the side that's moving away, which is red shifted, and you see it all together. So you get a wider line. And in MWU, we do some of these observations going farther out, deeper, longer, and we use the width of the line to measure the mass of galaxies. We weigh galaxies, which is kind of cool. But here in OPIS, we're just going to take the center frequency and use that to get a redshift. Okay, so 5 galaxies. So I'm probably going to remove the cigar. The cigar is not a Virgo galaxy, but there's another galaxy, Bode's galaxy, really close to it, tugging on it. And so you end up getting a very low Hubble's constant, like 40, where all the other ones are around 60 or 70. So I'll probably remove the cigar just like I removed the Virgo ones. But this list are the only spirals you could do in minute on, minute off. OPIS students don't have as much telescope time, so I needed to restrict it. So this is about placing the observation. We went through that last time. Here they indicate which galaxy they're doing. Very important they mark this correct because it sets the auto grading for the rest of the lab. Okay, 2 procedure sections. Once that was just collecting the data. They do that the week before. Going to measure Hubble's constant with the CDL and then with the CMB. So CDL, a little tutorial on how to do it, but I'll just show you. So here's Skynet. This one was NGC 253. I think this is the one I placed last week. And yeah, maybe last week, or maybe for my TAs before that. But anyway, here's the on spectrum. There it is. Here's the off spectrum. Gone. Here's on minus off divided by off. Again, the Milky Way line didn't cancel perfectly. The undulations didn't cancel perfectly. A little bit better in the green channel. And here you can see it's actually not just a top hat, but horn-shaped. And often these would be horn-shaped. If you have ordered motion, you're looking edge on, you get the Tully-Fisher horn-shaped profile. If it's more of a disordered dynamic, it looks more like a Gaussian. But anyway, to measure the center, we can go to live spectrum. These are Greenbank's tools. Down here, there's a magnifying glass, and you can just zoom in around this. And so kind of the center of this profile is right here, 1419.2. And get it to about a 10th. So once you have that frequency, they calculate the redshift. In lab 7, the redshift equation was in wavelengths. Here it's in frequencies because the tool. So here I walk through the conversion, and the unshifted frequency is there. So they put the emitted there, they're measured here, they're measured here, and they get the redshift of their galaxy. It'd be small, these are nearby. They got to do it to 5 decimal places. It's that sensitive. Okay, they got the redshift. So now the distance. Those are the two things we need. So just like in lab 6, we're going to give them a Cepheid. And these are made up Cepheids, just as I think they were in lab 6. For these nearby galaxies, you actually use different techniques to tip the red giant branch, planetary nebula luminosity function. There are different techniques that give you better distances. So I created some fake Cepheids that give those best known distances. I don't tell them that, but anyway, just like they did before, from the period, they get the absolute magnitude. They compare that to the apparent. They get the distance. Here's the distance equation. They're going to show their work. And then they calculate Hubble's constant. Hubble's constant is just c times the redshift divided by luminosity distance. They put that there. Should get something 60, 70. I think one's up around 90. An individual galaxy is not going to be perfect because it can be tugged on by things. Professional best determined value using all galaxies in both Cepheids and Type 1As, 73.4. This has been updated a little bit. I'll update it, but calculate percent error, put that here. Sources of error, they only use one galaxy. The redshift may not be purely cosmological, but contaminated by Doppler motions due to pulls by nearby galaxies. And we only use one Cepheid in the galaxy. There are presumably many Cepheids and other techniques. And the Cepheids are not, there's some variation. So M has some scatter as well. So if they get 3 of those 4, great. Then they calculate the age, which is just inverting Hubble's constant, multiplying by, they didn't include the time conversion. But here on like the early labs, this has example calculations for them. Scroll down. Age of the universe. So here's the megaparsec to kilometer and second to billions of years. I'll have them add that to the answer key. So the unit conversion, they can struggle, particularly weird units, normal units to weird astronomical units. So they have an example there. They'll get the age. Professionally best determined value is 13.8%. Errors, additional sources of error, and that is the expansion hasn't been uniform. And this equation assumes that it has been. Some deceleration, some acceleration. They mostly cancel out. It works really well. Okay, so that's measuring Hubble's constant age of the universe from CDL. Pause for a second. Any questions there? Okay.
Yes, I do have some feedback on this part.
Yes, go ahead.
I do believe some of the values in the solution might need some revision, I would say, especially for Phantom and Crowbar.
Okay, Phantom, what values were you getting for Hubble's constant?
Most of the students got values around 70, but the solution is 3.7, which doesn't seem to make sense.
No, they must have latched on to. They probably measured the Milky Way line.
Oh, no, this is not what I mean. I mean, the solution itself is giving Hubble constant to be 3.76.
Oh, in the auto grading.
Yes, in the auto grading. That's what I mean. Yeah, you can
Oh,
see it.
I see here. I see. I wonder if that changes once you enter values.
I don't think it does, because if they started by something that's different from the solution, it keeps marking most of their work as incorrect.
Okay, I will
And
go. So I ran this a couple times and no one told me anything was wrong. I haven't. So after WebAssign codes something, they usually have errors, and I didn't check this one. I just ran it, and no one reported problems back to me after 2 offerings now. So I haven't checked it. But now, if you could do me the favor of sending me a quick email, it'll get on my to-do list, and I'll try to get that corrected before the next
I
offering.
do have a couple of these. I will just send them in one email rather
Yeah,
than.
wonderful. Wonderful. Okay, CMB measurement. This one's pretty easy. Okay, so we have a map of the CMB in Afterglow. It says that you just go to the sample direct. Here, I'll walk through it. Sample directory, Astro 101 Lab, Hubble's Law, and you load it in here. And when you load it, it will actually start on the red layer. It tells them to click on the group layer. And so there's the whole Planck map right there. You click on this top one, it gets the red, the green, and the blue all together. You can zoom in and you can see these structures. Now, let me go back to the lab. And here, just to help them out, I kind of circle the typical size of these, but they're going to measure it with the ruler tool. So they come over here, they've done this before, and whether it's a red spot or a blue spot, there's one scale. You can see it. There's a very typical blob size in here, right? You're not going to say, oh, that's the blob size. There's a typical blob size that dominates. And so they're going to find a typical one and do a careful measure and take the value. This is only in pixels. So this came out as 4.4 pixels. They put it here. Each pixel is 0.21 degrees, so they convert that to degrees and calculate Hubble's constant using the equation we gave them. Just multiply their number of degrees in the typical blob by 82.2. CMB gets a value of 67.4. They calculate the percent error. Sources of error, they're only measuring one clump. CMB does analysis on the entire map, so all clumps at all scales. It's difficult to know where to start and stop your line. Full width half max, the edge, so that's a source of error. Difficult to know which is typical. And lastly, the equation itself is using the best values for all the other cosmological parameters. So that introduces an 8% uncertainty. But anyway, they get that in there. They calculate the age of the universe in the same way. Again, they drop the time conversion in the key. I'll get that fixed. Percent error. And then just to end it, we kind of an open-ended thing on the Hubble tension. I didn't include the error bars for the two, here are the professionally best determined measures. Their measures are going to be off by factors of 50, 100%. The CMB one, they can often be off by 100%. So they're not themselves going to measure the tension. Professionals have ramped up to this over decades. But I repeat the professionally best determined ones. I include the error bars this time. I didn't include them before because I didn't want them to get confused thinking that's the error bar they're supposed to measure. And I point out that even though they're kind of close, closer than your two measurements probably were, their error bars are really small enough that these are discrepant now at the 6.2 sigma level. So it's a big problem for cosmology. There can only be one expansion rate for the universe. And the fact that we measure two statistically different ones is a problem called the Hubble tension. And just like we had open questions about dark matter, dark energy in the previous two labs, we have them do quick search on Hubble tension and tell us what it could be. Most common explanations is it could be a systematic effect in one technique or the other. Kind of the common one that's put out there is maybe the type 1a supernovae change their properties at higher redshift under lower metallicity conditions. They think they've calibrated that, but it's the possibility. Another possibility is we live in a large void, like a crazy large void, in which case with less matter there, it'd be expanding a little faster, higher Hubble constant. But the void would have to be very large, like to the point of almost ruining the homogeneity isotropy assumption of the universe. Most people don't get that one. Or three, there's some new physics out there, and that's probably the first thing they'll read. Something we don't yet understand, and that's exciting. I didn't say it was a perfect model. I said it was a working model. And so there's still, it explains so much so well. We didn't even get into like nuclear abundances. That's a great success story of the Big Bang Theory as well. It does so much so well. It's got to be on the right track, but there are a few things that aren't working Hubble tension's one. There's one called large scale structure tension, where CMB is predicting more clumping than you actually measure much later on in redshift maps. The omega matter values are actually all over the place depending upon the technique. They're little tensions in the current model. There's still something missing. And people theorize that there could be early dark energy or dynamical dark energy and a zillion other possible explanations. But anyway, new physics. And that's the end of the capstone lab. Hopefully you see how it ties all the recent labs together. Comments, thoughts, questions? Okay. If not, then let me just say logistically, if you're offering it this semester, I'm going to be sending the post surveys around very soon and like probably Sunday. I've been writing a paper and I've been blowing everything off until I get to kind of a milestone point. And so everything I'm supposed to be doing is piling up and looming over me and but I should be at a stopping point in my paper Saturday. And so I'm going to start playing catch up. And I'll send out those survey links for the post surveys to send to your students and do, remind them periodically. And I'll give you some sample text and an encouragement video. This is where the money comes from that pays you in the participant program. This is actually what you're being paid for when you offer this to your students. You get $500 if you per year for doing this. You're being paid for trying to get high throughputs in your surveys. You also get paid for the training that you're doing now. And those checks won't be cut till summer, but so there's that announcement.
Sorry, Dan, I didn't quite catch that. Would you repeat that?
Yeah, so you're all getting paid for doing the training. I think it's $1,000 for the training, and then $500 a year for offering OPIS. But it's not just for offering it; it's for doing the pre and post surveys and being aggressive. Because what we really need are matched pre and post. So you want to get a very high yield on the pre. That's easier because the students are more enthusiastic at the beginning of the semester. At the end of the semester, through no fault of the lab or the content or your teaching, but they're tired. You're tired. And it's harder to get them to actually do these surveys again. And one's affective stuff like self-efficacy and attitudes. One is content knowledge. But you're welcome to offer extra credit. You're not technically allowed to require it due to IRB rules, but you're allowed to offer extra credit and incentivize it however you want. And you need to try very hard on that. And that information gets fed to our education research team, which is like, a lot of people do these pre and post tests and no one ever looks at them, or they make simple histograms. This stuff ends up in detailed analyses. They're publishing in PER, the leading astronomy education journal, physics education journal. And these wonderful results we're getting in self-efficacy are what going to help us win the next round of grants. The $500 ends next summer because the grant ends. So this is the last year to get the money. Hopefully that clarifies. Other questions?
I was going to ask earlier, is there any kind of working theory or on dark energy?
I've spent personally, I've spent the past 11 years working on dark energy theory as kind of my side passion project. And I'm very close. I'm probably 1 year away from putting out a series of 4 papers. So I do have ideas and opinions and thoughts, but kind of one of the leading ideas presented by theorists is one that I'm using in my work is early dark energy. If there is a period of dark energy around, we know dark energy is dominating now. You have the matter to dark energy transition in late universe. Phone's ringing. Let's turn that off. You can see Chapel Hill. I'll call them back. If you had dark energy around the radiation to matter transition, which is even before recombination by a little bit, it's like a few millionths the current age of the universe. If you had that then, basically you would expand the universe faster. You get to the CMB faster. And so the sound horizon, the little r in the numerator, theta is r over d, that r would be smaller because you didn't have as much time for the pressure waves to go. And so that would imply smaller thetas. You can't have smaller thetas because we measure them. They're 1 degree. And so the Hubble's constant dependence has to compensate. And so you would get a larger Hubble's constant, potentially consistent with that measured by CDL. So everyone treats the CMB as sacrosanct. That's the best measure. But if you have like a period of early dark energy, it's probably the CDL that's correct, and the CMB got it wrong. And so that's kind of my favorite theory. And they've tested it with empirical. We don't know what causes dark energy, so here's just kind of a empirical catch-all model. And yeah, it can explain the Hubble tension. The trick is to come up with a physical model. That's what I've been doing for the past decade. And I was just doing it for late time dark energy, but it turned out my model applied in the matter to radiation transition with no free parameters to work with, and it seems to be correcting the Hubble tension almost perfectly. So I'm pretty jazzed.
Interesting.
Yeah. That's where I'm going to put my money on early
That's one of
dark
those
energy.
things that we just kind of hear vague references to. We don't really ever get a whole lot of detail on.
Yeah.
So
Other than what I just told you, this falls under the category of shame on physicists. We gave up decades ago and turned our field over to the mathematicians. And so there's all sorts of string theory based dark energy and this and that and even just like inflationary theory, rolling potentials, they really don't correspond to anything physically. They're just mathematical things we jam in there and to make it work. And so I gripe a lot about how we've given up as physicists, given up our principled philosophical approach to doing physics, which comes out of quantum mechanics. Early quantum mechanics was so paradoxical, shut up and compute became
right.
the mantra. Don't think, just do. And because of that, we almost look upon philosophy driven physics with disdain. But really, I think it's what the field needs. And we need
Become
some.
more of become more of a number crunching field as opposed
Yeah,
to thought, speculative type of
yeah,
field. What
yeah.
actually explains these models?
Now, Newton was philosophy based. Einstein, very much
Right,
philosophy based.
right.
But after quantum mechanics, it became poo-pooed to approach physics in that way. And so we don't have solutions. We're kind of where we were 100 years ago, just with problems accumulating. Hubble
That's
tension is
It's
one
interesting
example.
that you mentioned that. I mean, that's kind of my, I kind of not having the extensive background, but sort of was general observation. There wasn't as much, theoretical um, progress in
The,
it.
the, the problem is our two pillars of modern physics, general relativity and quantum mechanics,
So I don't agree with each
work
other
perfectly. They don't get anything wrong.
independently of each other, right?
Yeah, I mean, you could even use them together uh, until you have a gravitational mass and a quantum volume. That only happens at the centers of black holes and the Big Bang itself. So as
Right.
long as you're not worried about those two things, you could work perfectly fine with these two theories. And so there's been no need to to
that was
solve the problem.
but that was the thing with Einstein and general relativity, right? I mean, Newton's theories worked just fine for every day.
Yep.
When Einstein comes along and says, well, what about, what's the, issue here? We just haven't
Hmm.
thought about it. And then, of course, for a long time, people said, well, yeah, that's just abstract. Who needs to worry about
Yeah.
that?
But even then, cracks were developing, like the precession of Mercury's orbit. People are
Right,
looking
right.
for another planet in there, and there's no planet in there to cause this precession. And in modern physics is the same way. Cracks are developing. The incompatibility of general relativity and quantum mechanics, the psychological error of time makes no sense. If you sat in our meeting with Daryl Jansen earlier last week, we had a great discussion about block universe and that kind of thing. What else is wrong with modern physics? The black hole information paradox. Information goes into black holes, they evaporate, random noise, and then where'd that information go? And firewalls and all sorts of things are wrong there. But in cosmology, it's the Hubble tension, the large scale structure tension. They're just problems everywhere.
These are the things that attract me to this field. So
Oh yeah, yeah. This is the stuff we spent our
stuff we
college
live
years
for.
talking about late at night in our dorm rooms, right? And the problem is modern physics is this great tower built on two disconnected foundations. And if you build a building on two disconnected foundations, cracks will develop. And so,
Having two different buildings and having a bridge across them,
yeah,
without really, you know, and trying to build that bridge across between them, and
the
like
trick is we have to replace the foundation
right.
without touching the towers because they make correct predictions. And that's tricky to change the postulates without changing the predictions. But I digress. This is fun stuff to talk about, but we're over, and I don't want
Thank you very much
I have
for
a
joining me.
I have a different question if I
Okay.
can.
Yeah, I'll stay as long, but
Yeah.
if anyone needs to leave, feel free.
Yeah, I want to know about next semester. So
Yeah.
I'm coming in late this semester, so I'm curious when
There'll
I
be a sign up sheet.
okay.
Normally I have it out by now, but
Okay.
I'm hoping the Sunday or shortly thereafter, I'll send out the sign up sheet for next semester. It will include the information about post surveys for this semester. And it's the same text I send every semester, and it's a Google sign up sheet. You just sign up and you put in the information that I'll need to create your WebAssign section and a guess as to how many students so I can start budgeting telescope time.
All right. Fantastic. And then I guess the last thing I'll ask is how long are you going to leave open this particular class? Because I want to keep playing with these
Right.
labs.
So you all have instructor access. So at the due date, it closes. You'll log on, you won't see it, but go to previous offerings.
Okay.
It only shows the current offerings. Go to previous ones, it'll still be there and you can still play with it.
Okay. Great. Thanks.
Believe you said we have the ability to assign ourselves additional hours in Skynet, or we need to hit you up,
Yes. So here, I'll pull up Skynet to show you real quickly.
and we can add our own students in there.
Yeah, so I can show you how to do that. Let me go to a group. Here's one. This is Edgecombe Community College Group. So you're down here, group management. To add students, you can manage members. Nope, sorry. Couple things you could do here. You can create user accounts. And so you can just create them individually here, give them a password that they can change later, a username, name, email, or you could just put their email in here, check this box so they get the invitation and assign their credits. So that's for creating user accounts. And to give more credits after the fact, you come to manage credits. You click on I've given the group enough credits for everyone plus some spare. So like when you're doing the R library observation, it's going to require extra credits. So you either give yourself or some student extra credits. Like this is the instructor here. You click on them, just gave the instructor 1,000 extra credits. or you may have a student who dropped the course and you want to take those credits back, put them in the general pool, then you can redistribute. So that's basically how that works.
Okay, great. Thank you.
When I send out the, no, you sign up and then I send out an email shortly before the semester saying your section's been created. And if you want to add students, I give you a little video that basically describes what I just said. And then you get another email either back to back or shortly thereafter. Once I have your student list with emails, then you get another email saying, okay, I've created your Skynet accounts. And that's the one that has the tutorial video for doing this group management, member management. Anyway, you'll get a sequence of little emails, some with videos that will be helpful to you.
Thank you.
Thank you.
All right. There's nothing else. Our training has come to a close.
Thanks, Dan.
And thank you.
you, Dan.
My pleasure.
I
Thank
appreciate all your help.
The
Thank you.
high school semester. Appreciate all the insight and help and everything. So look forward to continuing to work with you.
My pleasure. There'll be probably another sequence of these for MWU next semester if anyone's interested. And I'll email.
Looking forward to it.
All right. See you later.
Thank you.
Thank you.
See you.
Dan.